Hello everyone, welcome back to Chemical Process Design course video with me Anggit Raksajati, and we will wrap up our first case study about DME synthesis from methanol. And in this video we will talk about applying the heat integration concept into this process. So this is the flow sheet at the end of our last exercise. We finalized the rigorous simulation for the reactor. So we added the plug flow reactor and we get like the dimensions in terms of the diameter, the length, and the kinetics profile inside of the reactor. And then we also finish our rigorous distillation in terms of the amount of stages and then the hydraulic evaluation, such as the percent flooding at certain diameter and height. And also I expect you to already finalize the rigorous distillation for the second column. Okay, so now we still have one main things to do, which is to model or to design the rigorous shell and tube heat exchanger. And also we will apply a heat integration concept, because as you probably aware that we still use utilities for all of the heat exchangers. So for example, the E100, this is for a heater, so we use a steam for this heat exchanger. And then for E101, this is a cooler, and we still use cooling water. And the rest of the distillation column will still use steam and a cooling water. So that's why we now can combine or match the available hot and cold streams so that the energy recovery can be done and then the utilities can be reduced. So the looks of the flow sheet at the end of this video will look like this. So we will add a new shell and tube heat exchanger before the reactor, and the heat will be provided by the hot product gas coming out from the reactor because of the exothermic reaction. Okay, so we still gonna keep the preheater and the cooler, but obviously the Q100 and Q101 will be smaller because of the heat integration. So you will have to replace it with a shell and tube heat exchanger, then activate EDR, or the exchanger design rating, which is a very nice feature in HYSYS or in Aspen Plus, so that you'll be able to design the shell and tube heat exchanger. Even you will get the datasheet with the detailed dimensions. Okay, and once the sizing is completed, you can connect the main heat and material balance with the rigorous units, but it's again optional. And related with the heat exchanger design, this is the two main equations that you have to remember, so that you will be able to solve and troubleshoot or optimize the design. Okay, so in terms of the sizing, the Q, or the total heat exchange, would be U, the overall heat transfer coefficient, multiplied by the area of the heat exchanger, A, in square meter, and multiplied by the delta T LMTD, which is a log mean temperature difference. Okay, so, and then in terms of the heat that is required at each side of the heat exchanger, that will be the sum of the sensible heat and the latent heat, or the phase change. Okay, so what is really the advantage or the benefit of applying a heat integration? So we always go back to this onion chart about the hierarchy of the process design. We've already finalized the reactor and the separation and recycle system. Now we have to continue into the third and fourth layer, which is to perform a heat exchanger network so that our utilities can be minimized. So without heat integration, as you imagine that all the heating duty and the cooling duty requires the utilities, and after performing some heat integration, because of the internal heat recovery, now the hot utilities or steam or the heating duty can be reduced. The cooling duty in terms of the cooling water, for example, can be reduced as well. So the overall utility cost will reduce after the heat integration. Of course, there's gonna be some pros and cons that we have to optimize. Because of the addition of the new equipment to recover the heat, the equipment cost for the heat exchanger networks is going to be increased, but that usually will be acceptable as long as we design it properly. So because we also have to consider that once we perform the heat integration, the equipment cost for the utility will reduce. Why? Because, for example, now you will have a smaller circulation rate for your cooling water, and also you will have a smaller circulation rate for your steam generation system. So what will be the typical heat integration design? So this is just a starting point. Okay, probably the delta T minimum approach for the heat exchanger will be kept at about 10 to 15 degrees C. Okay, and if you wanna keep pushing those delta T to be as small as possible, you can recover more heat, but the consequence would be that you will have a bigger heat exchanger and it will increase significantly. So the capex will start to becomes drawbacks for your case. So that will be your typical delta T minimum approach for a typical chemical plant. But for a very specific case, probably where you have a very limited amount of utilities, for example, you want to build a platform in the offshore oil and gas production, maybe we can push this number even to 5 degrees C or even below that number to minimize the utility requirements. So we can check this design spec later on when we look at the composite curve of the internal heat exchanger. Okay, so when we set that the delta T minimum approach to be 10 degrees C, for example, we will have to make sure that the red line, which is the hot stream, will always be above the blue line, and the closest distance in one vertical line will be those delta T minimum. At this case, the delta T minimum is found at the end of the left point of this heat exchanger. Okay, so let's start with the simulation. So I will continue with the last exercise simulation with name DME rigorous. So at the end of those exercise, we've already added the PFR and then adjust the dimension to get to our process requirement, and we already added the first decision column complete with the hydraulic or the internal evaluation using a tray or a packing. And this is the exercise that I asked you to do for the second distillation column. I already finalized this, but I expect you to get complete and you get the results correctly for this second distillation column. Okay, so now we have to continue with the heat exchanger, and to do that I will add the pellet so that now I can add the new exchanger. So I will not use the simple heater and the simple cooler. Now I will use the shell and tube heat exchanger, and I will put it somewhere around here. Okay, so let me change my responsiveness first. Okay, save it. Okay, let me save as. I changed my mind. So instead of the DME rigorous, now I will save it, let's say, as a DME heat integration. Okay, and then I will edit my flow sheet so that I will have extra space in the recycle loop. Okay, looks good for now. Again, I will save it. So again, the idea is you want to exchange the Q100 from your preheater with Q cooler in your cooler. Okay, and first thing is you have to check where do you want to put your new heat exchanger. And the simplest way to do that is just by looking at the duty for each exchanger. Okay, for example, the Q100, the preheater, requires about 3500 kilowatt, while the cooler requires about 3000 kilowatt. By just looking at this number, you can already imagine how it would match, and where would the additional heat exchanger still gonna be required. Okay, so let's say we will have a perfect heat recovery where we can recover all the Q cooler over here for about 3000 kilowatt, and then you try to match those numbers to subsidize the Q100 for the heater. And again, just by looking at this number, you will not be able to completely preheat your feed from the mixer condition up until the 250 degrees C required by the reactor, because the number is even higher than the Q cooler. So the important thing over here is, even though we will add the new heat exchanger between the mixer and the reactor, we still require to keep the utilities heat exchanger, the E100. Okay, and that's still assuming the complete heat recovery. And let's say later on we realize that it's not gonna be possible to recover all the heat required over there. It's gonna be even logical to keep maintaining the E100. Okay, and also I will tell you that the technique that we will use in this video is not the complete heat integration such as the pinch technology. Okay, so I will explain about the pinch technology probably as the 4th or the 5th case study in this course, probably somewhere around week 10. Okay, so for now I just want to match these two main heat exchangers, and then I will design it using the EDR to get into a very detailed dimension of the heat exchanger. And before I do that, I'm just going to give you a quick preview of the energy saving or the energy analysis provided in HYSYS. Okay, so this is before any heat integration, and we can activate the energy saving features. And actually, Aspen will help you to identify some of the possible saving. Okay, so for example, now I click my energy saving, and we can check the total utilities, the heating utilities, cooling utilities, and carbon emissions or the carbon footprint, and the actual would be our current existing process without heat integration, while the target would be the theoretical maximum heat recovery identified by Aspen. So for now, I'm just going to snapshot these results, so I will be able to check it later after my heat integration completed. Okay, and then I think it's good if I can put it in my PowerPoint. So let's say I want to add it in my energy analysis before heat integration. Okay, we don't have to look at the number now, we will check on it later. Okay, let's go back to the simulations. Okay, also it's gonna be a good idea if you can open the two exchanges that you want to combine. Okay, so I'll open both of these exchangers, put it side by side. I go to the performance, and then I go to the plots. Okay, now you have something looks like a individual composite curve before it's being merged or combined. Okay, you can evaluate what happens inside of the heat exchanger, because the x-axis is the heat flow, the amount of heat exchange, while the y-axis is the temperature. And you will notice that we have some gradients in these two heat exchangers. Okay, and you can tells what happens in, let's say, in the first section of the heat exchanger where the gradient is very steep. This looks like a sensible heat transfer in a liquid phase. Okay, we don't really have any vaporization or any latent heat because the gradient is still very steep. And then in the center section of the heat exchanger, this is where vaporization happens. That's why the gradient decreases, and that will require extra attention during the sizing of the heat exchanger. And after it becomes saturated vapor, we continue to increase the temperature, so the third part is the sensible heat in terms of the vapor phase. And also in the cooler, you will all notice that we have two main sections. The last part, that will be the sensible heat, from vapor up until saturated vapor, and then you also notice that afterwards we will get a smaller gradient which will represent a condensation. Okay, and by just looking at this two composite curve, we already get the idea about where would be the challenge, because again probably the pinch point or the pinch location will be somewhere located in the vaporization zone, and that will help us to determine the allocations or the proportion of the preheater using the utilities and the complete heat recovery. So let me close that, and now I'm ready to size my heat exchanger. Okay, again, I don't want to directly replace my heat exchanger in the main loop, because just as my previous exercise, for sizing purpose, it's much safer if we locate it outside of the closed loop. Okay, so everything, some problem occurs, we can fix it usually more efficiently. Okay, so just double click your shell and tube heat exchanger. Now you will notice that we need to input a lot of things. Okay, so there are at least 4 streams that have to be connected: tube side inlet, tube side outlet, shell side inlet, and shell side outlet. Okay, and because of those requirements, now we have to think about the arrangement of the heat exchanger. Where would we put the feed? Will it be in the tube or will it be in the shell? And then the other parts would be for the hot product stream. Usually, again, you have to remind your heat transfer course what will be the constraint to select the shell and tube arrangement. Some of the things to be considered are the cleanliness or the dirtiness of the fluid itself. If we have a dirty fluid, usually we want to put it in the tube side. Why? Because it's easier to be maintained or to be clean. Okay, instead of cleaning the shell part of the heat exchanger. But actually, in this case, our mixed feed contains of methanol with impurities of water and DME will be mixed with the product of the reactor, which also contains these 3 components. Okay, methanol with less amount of methanol, water, and DME. So we don't really have much difference in terms of the composition of this shell and tube. So it's not likely to be the deciding point. Okay, and the other consideration, probably the operating pressure. We usually want to use the high pressure system for the tube, but again we don't really have much difference in terms of the pressure over here. It's about 14 to 15 bar. Okay, again that will not be the decision point for the shell and tube arrangement. The other case, usually you want to put your phase change in the shell side, but again we will likely to have phase change in both sides. So again, in this case, it's not gonna be very problematic for us to choose the shell and tube arrangement. So we can start with any choose that you want, and we can revisit it later if we have some warning. Okay, so again, I don't want to completely replace. So let me just use some technique to link the heat exchanger. Okay, wait for a minute. It's not really responsive, so I'm going to increase my responsiveness. Hopefully it will help with the speed of the simulation. Okay, so for sizing purpose, again I will do it outside of the loop. Now we just to imagine how these 3, 4, 5, 6 streams represents the actual process in the plant. Okay, the E100 will be used to preheat the feed from 30 something degrees C to a certain point, and then it will be continue in the new heat exchanger. So you open the new exchanger, so all 4 streams already connected, so the status change now into unknown delta P. So again, just for a starting point, you will have to provide the specified pressure drop in each side. Okay, so just use the typical pressure drop as we already conducted in the couple last video. Okay, and then there are a couple of heat exchanger model. For this first step, I will still use my simple endpoint. Okay, later on we will change it to simple weighted and regression entropy, but I will explain about it later. Okay, so I probably noticed where's the problem with my responsiveness, so I will disable the energy saving from now. Hopefully now it's faster. Okay, so what's the objective of this new exchanger? We want to provide the feed to be at about 250 degrees C before it enters the reactor, but we want to reduce the hot utilities from around 3500 kilowatt. In that case, we can say that let's say our tube would be represents the feed similar to a mixed feed composition. So I'm going to use a technique which is called a define from streams. So I will not put the number manually, but I will choose the define from stream, and it will replicate the numbers from my mixed feed. Okay, and then I can close it, and then for the outlet, of course it's gonna be the hot temperature, the high temperature at about 250, so that it will be ready to go into the reactor to replace the hot feed. Save it. Now you have to think about the arrangement. Okay, can we replace the feed of the reactor instead of the hot feed? Later we will change it with the stream 4. And for the shell part, again you have to imagine where would the stream represents this dummy stream 5. Okay, this dummy stream 5 is actually the hot temperature stream coming out from the reactor. So that is gonna be the stream 1 at about 365 degrees C. Okay, so instead of directly going into the E101, it will have to go to E102 first to recover the heat, to preheat the feed, and then if there is still any required cooling, it will be sent to the E101. So in this case, the stream 5 can be defined. So define from stream, so it's gonna be stream 1. Okay, save it, and stream 1, so you can go to shift T to make sure 37 to 250, 364 to 77.14. And there is a yellow line over here which tells you something is not really correct. Okay, so FT correction is low. This is actually very easy to be solved. Okay, when we have a very complex or difficult heat transfer, the correction factor of the heat exchanger will be low. And the easiest way to change or to fix it is you go to the rating. This is the default for the thema type. A would represent the integral bonnet, and E will represent 1 shell, and F will represent 2 shell pass. Okay, and that actually gonna help us because we will have extra area to be performing some heat exchange. So once we do that, usually it solves the problem. Okay, and we can go back with the performance again, and you notice that the minimum approach, it looks okay, we don't have any problem, and the green bar over here that looks like a reasonable heat exchange. And you can go to the plot, okay, to check the composite curve. You go to X, change it to heat flow, and Y, change it to temperature, and then go right click, graph control, because the color is not really easy to be read. So shell side, let's say it's blue. Okay, so see, this is very interesting. Why? Because it seems from the details of the performance we have a quite easy heat exchange, because the delta T minimum is about 40 degrees C and delta T LMTD is about 70 degrees C. But when we look at the composite curve, it's not actually realistic to have this kind of heat transfer. Why? We have a blue line above the red line over here, which is good and consistent with the endpoint. So at those endpoints, the hot stream will always be hotter than the cold stream. But you notice that in somewhere in the middle we have a temperature cross, because the red line at some section reach above the blue line. Okay, and that's not really possible, and that tells us that something is wrong with the setting of the heat exchanger. And this is the time where we have to change the heat exchanger model. So if we use the simple endpoint, usually it will ignore a lot of the problem in the heat exchanger. What does the simple endpoint means? So simple endpoint really means that Aspen will calculate the delta T LMTD only at these two endpoints, the entrance and the exit of the heat exchanger. Okay, so they will ignore the inside of the heat exchanger. So what needs to be modified is, now we will change it to simple weighted. Okay, let's see how to change it to simple weighted. Okay, change it to simple weighted, and then we have 5 intervals and 5 intervals. Okay, and we can check the results first. Okay, now we have a temperature cross, so it already gives us a more realistic representation. It's not really possible to perform this very ambitious heat transfers, okay, because the minimum approach now becomes negative. And you can check the plots. What does it means when we choose a simple weighted? Well, the easiest explanation, I'm going to add 5 vertical line just randomly. Okay, okay, by adding those 5 vertical lines, now from the entrance to the first line, that would be my first compartment, or the first interval, first section, and Aspen will calculate the delta T LMTD endpoint of section 1 only, and then section 2, Aspen will calculate the delta T LMTD for the endpoint of the second compartment, third section as well, fourth section as well, and up until the 5th section. That's why they will notice that the temperature cross will now occur somewhere in the second compartments. Even if we don't have a temperature cross, simple weighted will always gives us a more accurate results compared to the simple endpoint. Okay, so I will always recommend you to change it to simple weighted before we go to the sizing. So after this, I get the idea that we can preheat completely the feed from 37 to 50. Okay, so now I will open it. And then let's say we play around with the more realistic condition. Okay, so we already know that we want to use E100, so we can use it for a preheater. That means the stream 3, which would represents the feed before it goes to the reactor, it's not gonna be 37.58. Okay, so we can play around with the number and check later when it starts to prevent a temperature cross. Okay, so let's say 100. Okay, we still have a temperature cross. 140. It's still not happening, so I guess it's not really effective to manipulate the temperature. Again, use your judgment. The likeliest position is somewhere in the two-phase vaporization line. Okay, so we can play around with the vapor fraction to be faster with the arrangement. When I put 0, that means that's a saturated liquid. Okay, temperature is 153.3 and we still have a temperature cross. Okay, look, so it's still not good. Okay, so now at the other end of the vaporization, let's put 1. That means I completely vaporize my feed in the E100. Okay, and then I just use my internal heat recovery to increase the gas temperature from 153 to 250. Okay, we solve the temperature cross, but maybe it's still not optimized. Okay, why? Later on we will notice that the duty exchange is quite small. Okay, so this is, I guess, a good time for us to start connecting the heat exchanger with the main loop. Let me save it. Okay, let me think about the strategy. Okay, now I will connect my reactor. Instead of from the hot feed, now I will connect it to my stream 4. Okay, that's already at the same temperature, 250. I guess that would be a good first step. From hot feed, I'll replace it with 4. Okay, now my hot feed becomes free, or even I can connect my PFR with the same stream. Okay, stream 4. Okay, now I realized that we want to focus on the heat exchanger sizing purpose, and you notice that Aspen takes a lot of time to converge our PFR, which is not the main point of this simulation. So if you want to skip on that disturbance, you can double click on the PFR and then go to ignore it. Okay, once you ignore it, they will stop the calculation, and then we can activate it later after we finish with the simulation. The same thing can be done with the distillation. Okay, so you want to ignore all the rigorous just to prevent any disturbance. That's very fine. Okay, so let's save it. So now I have my temperature ready at 250 degrees C. Okay, and now it's going to be connected with the E100. So from 37 to 153, that will be heated using the utilities. Okay, let me just change it. So instead of the hot feed, now I have my stream 3 as the outlet of V100. Okay, there's a problem with the pressure. Okay, that's not really a problem. We can fix it. The problem, again, you can activate. Object is in the stream 3. The pressure is not consistent. Okay, it's calculated while we specified as 1500. The number doesn't match. So we just have to go to stream 3 and then we remove the pressure. We activate it. Okay, now it's fixed. Okay, so no worries. I will try to rearrange it to look nicer. Okay, not bad at this point. Again, I will save it. And then you can try to optimize the new heat exchanger. Looking at the temperature profile, it makes sense. Everything is still in dark blue in the main loop. Okay, so I can play around with the optimization of the heat exchanger. so it's green. So you see that we have a very big minimum approach or the delta T LMTD. So that's a very easy heat transfer, but that's probably not really ambitious heat recovery. You can check that using the Q100. Initially it's about 3500 kilowatt, now it's still above 3000 kilowatt. So even the decrease or the saving just under 20%. Okay, and the cooler, okay, we haven't connected, so the number doesn't change at this point. Okay, so we can try to find the balance, how much heat can be recovered by looking at the temperature minimum approach and the delta T LMTD. And you can try a different number, but I will try to be consistent with my previous slide where I state that my minimum approach would be 10 degrees C. Okay, so I will keep changing the phase. Okay, so you can notice that previously when we change it to 0, we have a temperature cross. Okay, so the vapor that represents the optimized heat recovery will be somewhere between 0 to 1. Okay, so let me change it to 0.5, see what's happened. Again, the temperature is gonna be roughly the same. Everything looks good. Dark blue, performance. Okay, my minimum approach already 8.5%. LMTD is 26 degrees C. So it's already too much of heat recovery if I want to be consistent with my 10 degrees C minimum approach. Okay, that means I can choose 0.5, it has to be higher. Okay, it has to be higher, so let me check 0.6. Okay, getting there, 10.8. So now I know my final number would be between 0.5 to 0.6. Let me try 0.57. Okay, getting there, 10.169. Okay, that means I still can reduce it slightly, 565. Okay, at this point I'm happy with this number because the number will change later on, so we don't really have to finish everything. Okay, so but if you want to get into a decimal as well, it's really fine, so you can change it again if you like. Okay, I guess because this is your first exercise, I will try to help you as detailed as I can. Okay, now it's getting there, already the third decimal, so I guess that will be close enough for me at this point. I will save it, and we can check the saving of the heater. Okay, we can check the saving of the heater. Previously it's about 3500 kilowatt, now it's about 2180 kilowatt. The saving will be around 40%, I believe. Okay, so it's quite significant, and we can continue with the other parts of the simulations. Okay, now we already connected the feed part in the tube directly into the process. What we haven't connected is the shell part, because previously we choose stream 5 coming as a defined from other stream, which is coming from stream 1. So it should looks quite close. Okay, but you already noticed that some of the number already changed because of the addition of the new equipment. The extra pressure already changed. Okay, the temperature slightly changed. So if you want, you can update the stream 5. Okay, how? Again, you go to define from stream, again choose stream 1, which will represent our updated shell stream. Okay, so now it should be identical. Okay, so what happens here? Save it. Okay, that's very odd. I can get my results. So let me just trigger the calculation. and then I revert it back. Okay, it's off. Okay, that's quite odd. Maybe I'll increase the additional number. Okay. Yep. Sometimes things like that happen, so we just have to refill the number, and even if we can give more tolerance, so it's safer. Okay, it's not really a big deal at this point, so we still gonna able to continue the heat exchanger design. Okay, what's next? We will link this stream 5 by changing stream 5 with stream 1. Again, I will save it. And okay, I think I changed my mind. I want to perform other things before I connect it with the stream 1. So let me try to size the heat exchanger first, so that you have a more understanding about the EDR. Okay, because it already looks alright, so now I'm going to size my heat exchanger first. How to do that? You can go to the design again. Previously it's already in simple weighted, so now it's ready for me to size the exchanger. Okay, I will size my exchanger and choose size interactively. If you choose auto size, you will leave everything to HYSYS, and even sometimes they will have some warning and some error that has to be corrected. That's why it's better to go to size interactively. For some of the older PC or the laptop, it requires a lot of time to finish the EDR, so you just have to be patient. Okay, and this is how it looks. So you can change the default number. For example, the thema arrangement. B is not going to affect the heat transfer, it's going only to affect the cost. So B is the cheapest one because it's integral with tube seat, so it can't be removed, so it can only be used for a clean fluid. C, that means it's a removable bundle, and again that's gonna be more expensive but it's easier to be clean. E, that's gonna be the shell arrangement. E would be the simplest one, while F would be our selection based on the previous evaluation. So I'm going to change it to F. The other part, you can change the tube diameter, let's say to 1 inch, 1.5 inch, the tube pattern, okay, and then the baffle and the materials. But I will use my default numbers for now, so let me click size, and HYSYS will try to calculate a lot of different variations that will best match our design. Okay, so the sizing finish, the shell is about 4.43 meter, length would be 3.6 meter, and then the baffle should be 4, the number of tubes should be 224. Excess surface, it's already quite good. It's quite close to 0. That means it's not oversized. Okay, the cost would be around 25,000 US dollar. That's the looks of the heat exchangers. That's our composite curve, and the tube layout can be shown over here. And if you're happy with that, you can accept the design. Okay, you can accept the design, and then you will notice that everything's look good in the heat exchanger part. Something is wrong, has to be fixed in the distillation, but at least in the heat exchanger it looks good. And you will notice that the temperature changes. Okay, why? Because the area provided is even bigger than our initial calculation. They have 1% excess. That allows the heating process to continue, and so that the temperature will start to increase. Okay, if you want to be very specific with this, you can fix it for now. Okay, so let's open the heat exchanger. If you still want to keep 250, at the outlet of the heat exchanger. Again, just remember everything we've done in this video, we mainly manipulate the vapor fraction of stream 3, okay, the in-between intermediate heating process. Okay, now if I want to get into 250 degrees C, but remember, you already override the exchanger now to be a rigorous shell and tube. It's not a shell weighted anymore. When it's already a rigorous shell and tube, that means the sizing results from the EDR already installed into this exchanger. So the area already fixed. So what needs to happen if we want to reduce the temperature? Okay, you have to imagine, okay, I guess that will be a good time for me to go back to my slide. Imagine Q equal to U multiplied by A by delta T. So the A will be fixed, the U roughly gonna be fixed. So what needs to be happen now if we have same amount of A but we want to get into a smaller temperature? Okay, so that likely we have to change the feed condition of those heat exchanger. Okay, so we have to change the vapor, and you have to imagine what would happen if you decrease the vapor fraction. If you decrease the vapor fraction, that means less vaporization will happen in the E100, okay, in the utilities part, but more vaporization will be done in the internal heat recovery. How would that affect the temperature of stream 4? The likely scenario would be if we reduce the vapor fraction over here with the same fixed area, that means our temperature at stream 4 will decrease, and that's our objective. So let's try to reduce the number to 0.56, for example. See the results into the temperature. Okay, now it's decreased to 50.3. So our guess is correct. I change it again, let's say to 0.559. Okay, it's quite close to our target. Okay, so I'm happy with the number at this point. It's already 250, back to our initial design. And again, you can check the stream 5 with stream 1, and if you want to update it, please do so. Okay, but if the number already identical, you don't really have to update it anymore. Okay, let me check the composition. Okay, it's still identical, so I don't have to update it, I guess. Okay, so it's time now for us to connect the shell part. So for the shell part, you have to look very carefully about this. Okay, I open again my worksheet, and initially my stream 5 now is has 3 blue colors. That means we have 3 independent variables. Okay, temperature, pressure, and the molar flow are independent variables. So what happens if I directly change it with stream 1? Okay, we can check between stream 5 and stream 1. Okay, temperature matches, mass flow matches, pressure slightly different. Okay, how about the composition? Okay, it matches, but the difference is for stream 1 we have a black color. That means it's a dependent variable. Okay, and that's not a good thing for a EDR calculation. Why? Because for EDR calculation, actually we have to completely define the tube fit and the shell fit at the same time. Okay, it will not allow the calculation to be completed if we directly connect the stream 1 into the heat exchanger. You can try it, it's going to cause you a problem. It's not going to converge. Why? Because we have to change some of this into a independent variable. And actually that's not really hard to do. Okay, if you remember my previous exercise, I can go to model palette and then go to manipulator, and we know a thing called a recycle. Okay, so in the recycle, now I will connect my stream 1, let's say to one recycle. And you can double check the recycle. See, every numbers are identical except for the type of the variable. Now it becomes a dependent variable. So it looks very similar with stream 5, okay? So let me change stream 5 into stream 1 rec. I go to my exchanger, design connection, shell inlet from stream 5. Now I'll change it to my new actual stream, do 1 rec. Okay, hopefully it will solve. Okay, what's happened? Okay, the temperature profile already changed, so I will not continue with this simulation. I will revert it back to my previous calculation. So I will connect it back to my stream 5. What's the problem? Okay, let me check. I get my fit correct at 250, but why now my reaction is not happening? Okay. That seems good. So what's the problem? I'm going to keep the number, Control C, and just try to trigger the simulation. Maybe I'll help with the complete vaporization first. Okay, that seems to work because now my simulation is already getting a high temperature. That means the reaction happenings. Okay, so and then I will connect back my reflux ratio. Okay, it's working. So now I can revert it back using the previous number, Control V. Okay, seems working. Save. Okay, really sorry for the interruption. It's good that I can fix it. Okay, 365 to 50, everything looks good. So let me think what's the problem previously. Okay, we have a slight difference in the temperature, so that means I want to make it as close as possible. So let me redefine my stream 5 with the one rack. Okay, the temperature changed, so I have to again update it. Okay, it's an iteration. I guess it's gonna be better to fix it now before it becomes a problem. So I'll fix again the vapor fraction. It's too hot. That means again I will have to reduce my vapor fraction. Okay. Okay, getting there. Okay, I guess that would be good. And then I will check my pressure. It looks good. I can save it. So I keep comparing between stream 5 to stream 1. By make sure that we get as close as identical condition as possible, it will help with the connection later. Okay, so if you wanna keep updating with the one rack, that's a good thing. Okay, so number keep changing slightly, but I guess it's getting into the conversion. Okay. Okay, so I'm happy with that for now. Again, I will keep updating my streams to be as close as possible. Okay, now once I update it, the temperature doesn't change, so I feel that now it's ready to be connected. Okay, let's try second try. Again, the concept is to replace stream 5 with one rack. Okay, to finish this heat exchanger. Stream 5, now I'll try to connect with one rack. One last save. One rack. Okay, looks good. Everything is in dark blue. Okay. And one last step is we will connect stream 6 into the heat exchanger. Why? Because it exceeds the internal heat recovery at 162 degrees C, whereas we want to send it to the first distillation column at 121.2. Okay, so the other 41 degrees C will be cooled down in the E101. Okay, and that's not hard to do. Hopefully, we just have to change the connection in E101. Okay. Design, now it enters at stream 1 at 365 something, which actually already sent to the heat exchanger, and then the outlet would be the cool product that is sent to the distillation column. Okay, so now we just have to replace stream 1 with stream 6. Save. Okay, seems very smooth. Now we can rearrange the simulation to look nicer. Okay, I guess for me at least that looks nicer. Okay, save it. Everything looks good. Okay. The duty already changed from 3500 kilowatt. The cooler already changed from 3000 kilowatt to 1700 kilowatt. So it decreased by more than 30%. Okay. And now I will check my products. 5 ton per hour DME at 99.5%. Looks good. So it's time for me now if I want to activate my regress. Okay, that took a lot of time. up until the 42 42nd, even up until 50 iteration is still not converged. Okay, let's wait because I don't see any problem with this. Okay, let's just wait, and then we can also, I'm gonna wait it so to just not to overload the simulation. Or even sometimes it's good if you want to reset the process. Okay, so I will reset the process. Maybe I have to change the size, the step. Okay, so let me ignore it for now, and I will change my step size to be even lower, but I will help the range because now I know it's gonna be around 5 meters something. So let me decrease the range of the iteration. Okay, reset. Our target is to get 82% conversion. Okay, if it's still not sensitive enough, I will again ignore it and keep decreasing the step size. Okay, so some of you may not even have this problem. Okay, so good for you. Because as you probably noticed that the change is not really much. Okay, so it's already around 5.89 meter in length to get into around 82% of conversion. Okay, I think I have another idea. I will choose my closest conversion rate, which is about 5.887, and then I choose Ctrl C. Then I will ignore my adjust. Then I will go directly into the reactor and update the length. Okay, and okay, checks the results. Okay, that's 83%, so 8.7, probably it's gonna be easier to manually change it. Okay, 5.8, 82%. Okay, so it has to be 7.8 probably. Okay, getting there. 5.79. Okay, one last trial. Okay, that's interesting. Why now it increases? Okay, I think I put the wrong number. Okay, 81.8. So we just have to increase it slightly. Okay. Okay, I guess that's good enough, 82%. Okay, so if we finish with the adjustment, we actually can delete it. Okay, so sometimes it's very annoying or disturbing. Actually, we already get our conversion, and we still get the number by changing it manually. That's fine. So let's save it, and then I activate my distillation column. Hopefully it will converge. Okay, good. And then last thing. Okay, looks good. Okay, now it's time for me to sum up this simulation. So everything's already finished. We already achieved the heat integration. We haven't actually applied it for the reboiler and the condenser. Let's keep it for the other case study. So now I will check my energy saving after the heat integration. Okay, and later I will compare it with the initial calculation. So let me delete that because we don't really have that stream anymore. So let's screenshot it, how the number change. Okay, and then I put it in my, even I guess it would be good to put it side by side. Before and after. Okay, you notice that the utilities cost decreases. Heating utilities decreases from 265 to 2.21. Cooling utilities decreases from 2.87 to 2.42. Carbon emission decreases by about, I guess, 20% from 3100 to 2600. Okay, so that's prove our advantage of having a heat integration. Okay, and if you want to keep optimizing the energy analysis, you can play around with these features, and then you go to the design change, for example, and let HYSYS help you to find the options to even decrease the total energy. No solution found to modify the exchanger to further decrease the energy. At exchanger, they search some solution. Let's wait. Okay, they have a couple of solutions, so I will leave it to you to explore, and whether you think that's gonna be a good idea. Okay, and just before concluding this video, I will also activate another feature of the capital cost estimation. So let's activate this economics. Okay, so once you finish with the all sizing, you can calculate the cost very quickly, just for a quick comparison purpose. Okay, so it's not detailed, let's say, to actually build the plan today. So it's just for a comparison purpose. So the capital cost would be around 5.7 million US dollar, and the utilities would be around 1.4 million US dollar per year. And if you want to see the details, just click on those icon, and then it will lead you to the breakdown of the costs for each equipment. Okay, so I guess that sums up my simulation and my first case study. I hope you enjoy this case study and challenge to explore more about the process design and process simulation. We will discuss about it in the class, and also see you in the next video about the next case study about the synthesis of acetone from isopropyl alcohol. Okay, see ya.